Hi, everyone. So I'm Filip. I work as an ML DevRel for Superling. So I've been an ML engineer and a data scientist before. And now I am working on something new and different that I'll show you here today. And the aim today is to do three things. So the first one is to kind of showcase the problem and showcase how the modern day situation is with search. What are the user expectations and what is the problem? Then the second thing I'll introduce will be our solution and our approach to this problem, and also what we're doing kind of from an open source perspective, some resources that we have out there. And the last part, my colleague Ben will introduce, will be around kind of the applied situation of Superlinked and kind of the production use case where we can actually see the impact. So in the age of LLMs, search has changed and user expectations have changed drastically. Nowadays, probably due to ChatGPT and due to kind of the, I guess, the direction of the whole industry towards generative AI, users now are more used to inputting longer queries and explaining things with text, like what they like, what they don't like. So we're moving away from kind of just like filters and keyword search. So that's what kind of we need to be prepared for if we want to stay competitive in the market and have a recommendation system or search system that can kind of satisfy this consumer need. An example query that people would input nowadays is something like this. So this would have stuff around location, features, price. So a lot of different things in one query. And usually what kind of the standard way would be, let's use an embedding model, embed everything as text, we get the vector embeddings and just map them into a vector space. And all good, all sorted, we're done. However, this is most likely not enough. The problem is that something like this happens. So this data is multimodal. There are objects of different types. Some are numbers, some are queries related to time. For example, if you say popular hotels, that would include a component that's related to time. What's popular today is not what's popular, what will be popular next week or what was popular 20 years ago. So as we dive deeper, things get more complex and more complex as we look into different data types. One example that we use to showcase this is, for example, numbers. If you use any OpenAI embedding, the latest one, and you try to embed the numbers from 0 to 100, and then you look at the vector similarity between the embeddings, you will notice that it's not quite granular and linear as you would expect, meaning that, for example, the number 40, the two most similar embeddings are not 41 and 39, but some other numbers like 45 or 50. And this is due to kind of how the LLMs map numbers into this latent space and so on. And this is just one example that you can test out very quickly, but this problem extends to a lot of other data types and objects. So, for example, to kind of broaden the picture a bit, you can see on the right side we have this number example that I mentioned. But for example, with also queries like recent or near or popular and so on, they have a fuzzy preference in them. So this is not something that is like a binary filter, like something is popular or isn't popular. And if you kind of do this manually in this way and filter things in this way, you're missing out on the nuance and the granularity of something like this, which in itself would be a sigmoid function, let's say, where you have something that's a bit more popular, a bit less popular, the least popular. So it's important to be able to encode this in your search systems. And also, in theory, yes, you can kind of fine-tune your own models, but when the number of objects increases and different scenarios, this is not as straightforward. And in kind of a production setting, what you would end up with is something like this, where you have your data in different SQL databases, in different sources, both structured, both unstructured. You have images, you have text, you have certain tables in one part of kind of your whole infrastructure, another in another. And this problem gets worse and worse, so you would have to do something that would include like multimodal, but also hybrid search, so a bit of semantic, a bit of keyword, but then you would want to do some boosts to kind of encode this nuanced differences, different coefficients, then probably do re-ranking in the end. So if you want a production use case, there are a lot of steps that you need to do. So having noticed this problem, we've decided to introduce a slightly different approach that kind of solves this problem and gives it a bit more of a general solution. So we call this approach a mixture of encoders, and we've built a full framework with its own DSL. And we basically, what we do is kind of use specific encoders for different data types. So as you can see here, a query like popular blue shirts below a certain price, we would use a number encoder to encode the number. We would use a data encoder. We would use a category so that this links up with kind of your inventory and what you're trying to do in terms of your products and For You pages and so on. And this, of course, does not end with only 4 types of encoders, but this can get kind of deeper and more complex. And of course, we have a semantic encoder, which can be any kind of model. We work closely with Redis and Quadrant, and we also include click counts and product kind of databases and user interaction. So this means the query will be decomposed into something like this, where we would encode the price with a numeric filter, a location kind of encoder, a semantic encoder, category, and numeric. And this is kind of the situation with the production use case, where this is the kind of data you would come up with. So we work with this kind of data, including images. And this is a bit the more complex overview of the architecture, but we also have a booth, so we can talk about different things later on. I won't go deep into this now. And the idea is to end up with a vector-first approach, where you have a big concatenated vector, where all of these sub-encoders create sub-vectors, for which you can do filters, weightings, you can push different business logic based on what you're trying to do, and then end up with like a vector-first approach that has all of these nuances encoded within this vector, and then you're able to do just like approximate nearest neighbor search with all the relevant stuff. And this would mean no re-ranking also. How do we evaluate this? So I'll speak briefly on kind of benchmarks. This is one open source resource that we have. So all the popular benchmarks do not include multimodal data. So basically, we can see that MTEP has a very also like a fuzzy metric where it combines different values. BR is nice, but it kind of depends a lot on synthetic queries. And then again, none of these have metadata, none of these work with kind of different data types, which we wanted to kind of solve. So we decided to work on building our own benchmark based on the Wayfair once dataset. And we're using LLM as a judge with pairwise ranking as a way to kind of do the labeling in a kind of more cost-effective way. And we'll have this published soon, and we can also talk about this more. And we also have an article on our blog, which is also a resource you can have a look at, where we compare this mixture of encoders approach to BM25, Colbert, cross encoders, so all the popular techniques, but then we will release a proper benchmark fairly soon. We have an open source repo, so you can also access this, have a look at the code. And we have also a VDB comparison table. So we are a layer on top of vector databases. So you can kind of use us with any vector DB. We work closely with Redis and Quadrant, and we've kind of integrated at a very large scale, so millions and millions of vectors. And now my colleague Ben will speak a bit about the impact and the production use case of Superlinked and what our results have been.
Thanks, Filip. So hi, Ben, one of the co-founders of Superlinked. I'm more on the commercial operations side of things. So you got the technical spiel of Superlinked and the theory, and I'll talk a little bit about how does it actually look in production when we work with clients, what kind of results we've seen, and what kind of benefits they've seen working with Superlinked. Yeah, excellent. So some on the benefits, first of all. So first of all, time to market or time to launch AI-powered or conversational search. You can get to production in weeks. Of course, there is the whole feature engineering part of it, but basically you test your approach in a notebook, compile it to a cloud API, connect it to your application, and you're ready to go. Multiple use cases, so search is one. Recommender systems is another one. The retrieval part of RAG, analytics, fraud detection, a lot of different use cases where vector embeddings can be helpful. Improve retrieval quality. Filip touched on this. By encoding a lot of different data types in one vector space, you get better quality. Even by using LLMs, which are maybe less performant on their own, but with combination of other types of data, you get better results. And of course, efficiency and cost as well. You can update partial vectors. You can switch VDBs when you need to. You can use an expensive one for real-time use cases and maybe a cheaper one for less time-critical ones. A real-life example, right? We did a search of sparkly dress for a Christmas party under 100. This is a well-known large UK retailer website. As you see, not so many dresses, and this is what Superlinked retrieves in our demo e-commerce website. You can see that the results are better, and that, of course, delivers customer impact and revenue impact. So just to talk a bit about a case study that we did. So this is with Brand Ali. This is a relatively large e-commerce retailer. They do flash sales in the UK. This is the architecture of how it looks. We connected StreamCap, a real-time pipeline through Kafka to get user events, get user updates, and also vectorize the product catalog. Stored it all in Redis and gave an API for the application to present the results to the user, and achieved 77% increase in conversion rate, 68% in average order value, and then, relatively low latency, so no impact on user experience, beyond, of course, getting better products for the users and increasing sales. That's it. Thank you very much. Any questions?
All right, thank you very much. So we've got time for like 3 or 4 questions. Although I will start with an online question. Oliver asks, I'd be interested in cutoff thresholds. Does this approach give a fixed nearest neighbors result set, or figure out if even the nearest result is not relevant, a no-hit, or when the distance is large enough to be considered wrong or irrelevant?
So sorry, at the end, if it's with the large enough, I didn't get that part of the question. It said.
Where was the start? Give a fixed nearest neighbors result set, or figure out if even the nearest result is not relevant. Mm-hmm. Or when the distance is large enough to be considered as relevant or irrelevant.
Yeah, so I guess this depends on kind of how you construct the concatenated vector. So we use approximate nearest neighbor search, so you wouldn't kind of, when you set this up and you have all the relevant subvectors, and your query vector is also encoded in the same way. So it depends on the use case. You can kind of prioritize different subvectors, so you wouldn't kind of end up in a scenario where there are no results or the distance is too high, because it's usually when you search, for example, for something related to the pricing, you would kind of bias the vector that is related to price to kind of have those neighbors closer. So yeah, we're able to do that as far as I understand.
All right, thank you. Is there another question here? Yes.
Thank you for the presentation. It was really interesting. Just a quick question was like, you mentioned that it's mostly about the longer queries where users are very intentful. But what about the shorter queries? Because in many of our websites, we do see that the shorter queries are the popular ones. And will BM25 still overpower there?
So yeah, the thing is that with our approach, you're able to have that benefit. So you can work with shorter queries, but also leave the option of like adding complexity further on and iterate on that quickly. So you can do BM25, but then after a while, you'd probably want to implement semantic search eventually, or you would end up doing hybrid search. So our point is that we want you to kind of spare you of this extra steps. And also, you can include different data types. So for example, you can do shorter queries, but work with interaction data and click data. So that can be how your concatenated end vector is constructed. So it's very dependent on the business problem that you can pick kind of how you do this.
Maybe just to add to that, what we've seen in production with clients is that you can do triage, right? So if the query is simple and you don't have those components, yeah, just use your regular search solution, BM25. But once the query becomes longer, it includes components which refer to price or refer to recency or refer to category or attributes which are more complicated. Yeah, then it goes to superlinked. And we have this NLQ component that takes the query and basically breaks it down or converts it to a vector embedding of the same structure as your data is. And then it's just a simpler vector similarity search.
Okay, I'm sorry. Time's almost up. I would prioritize one online question because they can't come here and ask in person. The question is, which LLM do you use as judge?
So for the benchmarking efforts, I assume, I'm not sure which LLM we use, but also the idea, I'll expand a bit on that, was that if we just kind of prompt an LLM, for example, to say rank these items in a certain way, there is not enough like consistency in this approach. So what we are doing is we're doing kind of like a pairwise comparison where we compare one ranking to another and then do bubble sort to kind of do the final ranking. But basically that's the kind of the way we do it. I'm not sure what LLM we use, but the point is that we're not doing kind of, this can be done with different LLMs. The key thing is that we're doing pairwise comparison and then bubble sort to get the ranking rather than just the raw output of the LLM. But we'll have more details on that. We'll open source this, yeah.
Right.
And we have a booth also, so yeah, feel free to come down and chat.
Exactly. If you have any other questions, remarks, or just want to chat, go downstairs to the bar area and visit them at their booth. And now, please give a warm hands up for our speakers.